So the next part of the paper is called Statistical Validity, a tutorial. And it's going to start out talking about the problem of multiple comparison, give some examples of multiple comparison or multiple testing problems in machine learning, and then go on to talk about independence and lack thereof. So, go to the paper. So I'll read from the paper now. Statistical validity, a tutorial. Statistics offers many tests that are designed to measure the significance of any difference between two or more quote unquote treatments. Treatments is a term that comes from biological and medical practice. So traditionally treatments might be something like putting one fertilizer versus another on a plot of land. Statistics offers many tests that are designed to measure the significance of any difference between two or more treatments. These tests can be adapted for use in comparisons of classifiers, but the adaptation must be done carefully because the statistics were not designed with computational experiments in mind. What does he mean by that? I think what he means is something about the many different comparisons that we're doing in the typical machine learning paper, many of which we don't actually publish because they don't end up in the paper. That's a problem. So the problem is even worse than it might look. Okay, back to the paper. For example, in one recent machine learning study, 14 different variations on several classification algorithms were compared on 11 data sets. This is not unusual. Many other recent studies report comparisons of similar numbers of algorithms and data sets. All 154 of the variations in this study were compared to a default classifier, and differences were reported as significant if a two-tailed paired t-test produced a p-value less than 0.05. This particular significance level was not nearly stringent enough, however. If you do 154 experiments, then you have 154 chances to be significant. So the expected number of quote unquote significant results at the 0.05 level is 154 times 0.05 equals 7.7. Obviously, this is not what one wants. A little aside here, bear in mind that though that would be 7.7 results that look significant, but in fact, you just came up with them by chance. Okay, obviously this is not one wants. In order to get results that are truly significant at the 0.05 level, you need to set a much more stringent requirement. Statisticians have been aware of this problem for a very long time. It is known as the multiplicity effect. And I'll throw in there, this is also the multiple comparison problem, the multiple testing problem. At least two recent papers have focused their attention nicely on how classification researchers might address this effect. And he quotes two papers here. Take a look at the manuscript if you want to see who those are. And I want to say that this is a wonderful case of citing other people's work in a complementary way by use of the adverb nicely. Okay, so at this point, the paper goes into basically an explanation of the math behind the multiple comparison problem in more depth than the example that I gave above of the 154 different comparisons that just by chance alone would yield about 7.7 significant outputs. You probably already know how the mathematical argument here goes. He states it very nicely in about 3-4 paragraphs. So where I'm going to pick up, he moves on to talking about independence and actually the lack of independence that something like a t-test assumes. So we'll go back to the paper here. The above argument is still very rough because it assumes that all the experiments are independent of one another. When this assumption is correct, one can make the adjustment of significance described above, which is well known in the statistics community as the Bonferroni Adjustment. A little aside here, basically the way the Bonferroni Adjustment works is you take the alpha level you're looking for, this would be 0.05 typically, and you divide that by the number of tests. So if you're doing 154 comparisons, your threshold for significance that would be equivalent to a p-value of 0.05 would be 0.05 divided by 154. Okay. Back to it. Oh, one more aside. I actually did not realize that Bonferroni requires independence between the tests. So that's a new one on me. I'm going to start this paragraph over. The above argument is still very rough because it assumes that all the experiments are independent of one another. When this assumption is correct, one can make the adjustment of significance described above, which is well known in the statistics community as the Bonferroni Adjustment. When experiments use identical training and/or test sets, the tests are clearly not independent. The use of the wrong p-value makes it even more likely that some experiments will find significance where none exists. I think by wrong p-value, what Salzberg means here is an unadjusted p-value. Nonetheless, many researchers proceed with using a simple t-test to compare multiple algorithms on multiple data sets from the UCI repository. Think of this as any set, any collection of shared data sets. And he gives an example of a paper here, Wetschurek and Dietrich, 1995. Although easy to conduct, the t-test is simply the wrong test for such an experimental design. The t-test assumes that the test sets for each quote unquote treatment, that is each algorithm, are independent. When two algorithms are compared on the same data set, then obviously the test sets are not independent since they will share some of the same examples, assuming the training and test sets are created by random partitioning, which is the standard practice. This problem is widespread in comparative machine learning studies. There's a parenthetical statement here. One of the authors of the study cited above has written recently that the pair t-test has, quote, a high probability of type 1 error and should never be used, end quote. And there's a reference here to a paper by Dietrich in 1996. I'm going to read that again, that quote, a high probability of type 1 error and should never be used. Never is a big word. We don't use it too often in science, right? Back to the paper. It is worth noting here that even statisticians have difficulty agreeing on the correct framework for hypothesis testing in complex experimental designs. For example, the whole framework of using alpha levels and p-values has been questioned when more than two hypotheses are under consideration. Certainly you could say that that's the case in natural language processing. If you figure that by hypothesis, what Salzberg means is not what you might think of as a scientific hypothesis, something that posits causality, but rather a statistical hypothesis, something that posits a relationship between two different populations, or not different populations, right?